Guys, welcome back to another video, and today we're going to be working with square roots. Anyways, jump right into it. So what is a square root? So a square root is a question. What do I mean by a question? It's asking what two numbers will times by each other to give you a certain number. Here, let's think about it like this. So square root of 25. In this notation, which is the square root, looks like a long division sign. This is saying to us in English, the square root we see here, it says what two numbers, two identical numbers, will times by each other, okay, will be multiplied by each other to give us 25. We know what those are from basic math. 5 times 5 is equal to 25. So we answered the question. The question for a square root is what two numbers, two identical numbers, will times what we have in the inside. It's 5. Now, why didn't I write 5 times 5? Why did I only write 1 5? It's because in square roots, you always think about pairs. Okay, so when it comes to square roots, they're actually the opposite of exponents. So you have this 2 right here, this invisible 2. It depends. If it's square root, it's a 2. If it's a cube root, it's a 3. Anyway, so if we break this down, we know it's 5 times 5, and we know exponent is repeated multiplication. So this would be, right here, would be 5 squared, and we put it under a square root. This is the identity. Basically, when you have something like this, a 2 greater than less, it has to be equal. The inside, the 5 squared, the squared, has to be greater than or equal to the 2 on the square root. What's inside is called the radicand. So when the degree of whatever is inside the radicand is the same as the square root, you just cancel out and you get 5. So that's the identity. So there's 2 ways to think about it. But it's not always this simple. For example, let's try another one before I introduce the idea. So what about the square root of 16? So again, what two numbers times to give us 16? What two identical numbers? Not numbers. Not 8 times 2, no. 2 identical numbers. They have to be the same. This would be 4 times 4. If we put it under the square root and we simplify, we get 4 squared to the 2, and we just get 4. Great. So square root of 16 is 4. What about the square root of 32? Do you know two numbers that times to 32? Two identical numbers? No. Well, let's see. 8 times 4 is 32. Are they identical? Are they the same? No. What about 6 times 4? Oops. Sorry about that. Where were we? I'll just finish it anyway. Square root of 32 and what is the square root of 32? We don't know, because the square root of 32, there's no identical numbers that times to give us 32. There's no 8 times 4, those aren't identical. 4 times 6, those aren't identical. 12 times 2, those aren't identical. So we introduced an idea from before. Remember perfect squares. Perfect squares means we have something like the square root of 16. This is perfect because there are two numbers that exist, factors, okay, that times to give us 16. They're the same, equal factors. Here, these aren't equal factors. They're not. So what can we do? Well, there's this method called prime factorization, and it involves the use of prime numbers and perfect squares. So if you don't know what a prime number is something that it can't be divided, only divided by 1. So for example, if you have like the square, you can't simplify it more. Like for example, if you do 6 times 2 and you break, if you do 6 and you break this down to 3 times 2, these are prime numbers. They can't be simplified any more. What can you do? Integers. You can do 1.5 times 1.5, but these aren't integers. And same here. This would be, I don't know what this one would be. But anyway, you get the point. So they have to be integers. So when we're doing the square root of 32, what we can do is we can do this flow chart. We can break it down into, we can simplify it basically. So let's go through it. So the square root of 32 is the same as 8 times 4. Now, when you're doing this, you want to choose like the multiples that have perfect squares. See how I did 8 times 4? 8 isn't a perfect square, but 4 is. Square root of 4 is 2. We're going to use this a little later. So let's continue down. We're going to continue to do this until we get prime numbers. Numbers that can't be divided up using like decimals. So we're going to do, again, let's do 2 times 4. Now, I like to do this. I like to keep the ones that I know that are perfect squares on the right side. And I group them. Because remember, when we're doing square roots, we group them. Pairs, squares, pairs, repeated multiplication. So anyway, we can't break this down more than this. We could, but they wouldn't be perfect squares. So let's just leave it like this. So now we circle everything. Okay? You circle everything on the right here, and you circle your last row. You don't circle this 8. And also you can confirm this because if you do 2 times 4 times 4, you'll get 32. So 8 times 32. So make sure you ignore this 8 because you see how we broke 32, the first step. This was the first step, and this is the second step. We broke it into 8 times 4, right? And the second step we didn't break down the 4, we only broke down the 8 into 2 times 4. That's why we're doing it like this. So anyway, when we group these up, and it's put in the radicand, we get 2 to the 1 times 4 to the second power. So now the 2 goes away because you know the identity, so we just get 4 on the outside, and the 2 to the 1 is less than the radicand. The degree of what's inside the radicand is less than the square root, the power of the square root. We can't go out, so that means we stay inside. So we just get 4 times the square root of 2. Great. Look, it's a little difficult, but once you do it, you'll see how it works. There's another one. Let's do the square root of 45. Great. So how do I do this? Let's break this down. So I'm going to use 5 and 9. Okay, now because square root of 9 we know is 3, but let's break this down a little more. So so 5 can't be divided anymore. Okay, so we just break down 9 to 3 times 3. So now we group up our terms, okay, and we get 3 squared times 5 to the second power. The 2's goes away, so we just get 3 times the square root of 5. Great. So if you want to shortcut anything that's in pairs, goes outside right away. But there are some like situations where you have like to the third, so one of them stays inside. So let's do another one. Let's do the square root of 75. So what's 75? We can do 25 times 3 is 75. Then we can break this down to 5 times 5. Now this is a pair, this is not a pair. So then this just becomes 5 times the square root of 3. And you can always check this because if you do the square root of 75 in your calculator, you get like approximately 8.6. And if you do 5 times the square root of 3, you get the same thing. So that means you did it right. Anyway, let's do one more. So when we see something like this, and it's not a perfect square, we don't know two numbers multiply, we use prime factorization. So again, so what's two things that add to times 98? I think 12 times 9, no, 12 times 8, I believe. No, that's 96. Let's see, 98 times 2, 49. So 49 times 2, and let's break this down to 7 times 7. Group up the pairs, and we just get 7 square root of 2. Great. So now, this is going to be important. Prime factorization, very important. So now let's do some identities of square roots. So let's first introduce the multiplication division identity. So you have the square root of a times the square root of b equals the square root of ab. Then you have the division. This is the multiplication. And division is the square root of a divided by the square root of b. Whoops, the other way around. The square root entire. This is notation for a huge square root. Square root of a divided by b is equal to the square root of a, the individual square root, divided by the individual square root of b. And this is the division property. Division. So let's work some examples. So let's do the square root of 6 times the square root of 24. So what does this equal to? So simple. We just, first of all, let's do prime factorization when we're done. Always want to do prime factorization, rationalizing with these things to get in the simplest form. But first, let's do this applied identity. So we know the square root of 8 times the square root of b is equal to square root of ab. Let's call a equal to square root of 6. And it's called b equals square root of 24. And it's just times the inside. So 6 times 24 is 144. So square root of 6 times the square root of 24 is equal to the square root of 144. And it turns out 144 is a perfect square because 12 times 12 is 144. So that means the square root of 6 times the square root of 24 is equal to 12. There we go. Let's try another one. Square root of 10 times the square root of 40. So how do you do this? We just times the inside, so it becomes the square root of 10 times 40, which is, I believe, 40,000. No, 400. So square root of 400. So it's 400. Does it have a square root? Let's check. So 400. Yep, it's 20. You can choose in the calculator. So square root of 400 is equal to 20. So that means the square root of 10 times the square root of 40 is equal to 20. Okay. Now let's try division. A division property. So you have the square root of 18 times the square root of 2. Okay, so how do we do this? So we can break this down. So what's the square root of 18? Well, is it in simplest form? No, so we have to use prime factorization. So we can do 9 times 2, and then 3 times 3, and we're going to get 3 root 2. So we get 3 times root 2 divided by root 2. Let's replace. So now, when you have something like this, okay, if you notice it says 3 times the square root of 2 divided by square root of 2, which means it's like saying 3x divided by x. So we can just cancel out the x's. Honestly, with something like this, they're like x's exactly when they're the same, so it just cancels out. So it becomes the square root of 18 divided by square root of 2 is equal to 3. Okay, good. Now let's work with another one. What about the square root of 9 divided by the square root of 3? Or no, square root of 16. So square root of 9 is 3, and the square root of 16 is 4. So square root of 9 over square root of 16 is 3 over 4. Great. So now, let's do the addition and subtraction identity. So addition and subtraction identity says, the square root of a plus the square root of what was the identity? Well, I'll write it my own. So 2 times this, or we can represent like set notation. So n times the square root of a plus n times the square root of b is equal to n square root of a times n square root of b. Okay, now this is not the identity. The real identity is n times the square root of a plus y times the square root of a equals n plus y square root of a. So basically, the only way these rules are kind of confusing, like this addition and subtraction, because it's kind of like making a common denominator and like the 3x thing. But anyway, the best way to think about it is to say 2x plus 3x is equal to 5x. No, do we do x squared? No, we just add the coefficients. The same idea here. If we have the 3 times the square root of 2, same thing as 2 times x, 2x, 3 root 2. Say 3 root 2 plus 4 root 2, you just get 7 root 2, right? So it's the same idea here. Same with subtraction. So the only way you can do this is the roots have to be the same. Okay? Think of the roots when you're doing this. When you have a number times a root, think of it as a variable. If the variables are different and you can't reduce them with prime factorization, you cannot combine them via addition subtraction. With division and multiplication, it doesn't matter. You just do the multiplying and dividing inside. It's simple. With addition and subtraction, you have to make sure the radicands, the number in the radicand, is the exact same for both coefficients. So let's go through some examples. So 5 times the square root of 3 plus 2 times the square root of 3. We apply that identity, so this becomes 7 times the square root of 3. Because remember, the identity was n times the square root of 3 plus y times the square root of 3 is equal to n plus y times the square root of 3. Or let's say it would be 5x plus 2x equals to 7x. Instead of x, we call it root 3. Same idea. So let's try another one. So 7 times the square root of 5 minus 4 times the root 5. This is going to be equal to 3 root 5. So now let's try one where it's not possible to subtract. So we have 3 times the square root of 2 plus 3 times the square root of 3. So what comes of this? Well, we can't combine the insides because they're not the same. And we can't combine the coefficients because they're not the same, because this is like saying 3x plus 2y. Can we combine them? No, not the same. So this just stays as the answer. Let's do another one. So let's do 10 minus 4 root 10. Can we combine this? No, it just stays the same. So this, just because this is 10, basically. Let's think about this. So the square root of 1 is 1. So basically we can write like this. Can we combine these? No. So this just becomes 10 minus 4 root 10. This is the answer. So now let's do a few more examples. A little hard example because I want to make sure that you have a strong foundation in these. Bring them up. Okay. So now let's do this one. 6 times the square root of 20 minus 2 times the square root of 45. So how do we do this? Well, are the identity, are the numbers inside the radicand the same? No. So does that mean we can combine the coefficients? Also no. So what can we do? Do we give up? No. If you look, these aren't prime numbers. Remember, prime factorization, the remainder from what we do, if the inside of the radicand is a prime number, like a square root of 3, we can't simplify it further without using decimals. Only like using integers in this stage of math. So, we give up. We have something like that. Like if we had 6 root 3 minus 2 root 2, we'd give up at that point. We wouldn't even bother because we can't combine them. We can't simplify the number in the radicand. But here, in the example I gave, turns out you can. So what I'm going to do is I'm going to do the prime factorization, and I'm going to show you something that some people get a little confused with. So anyway, so 6 times the square root of 20. I'll do one at a time. Let's break the square root of 20 down. So it's 10 times 2. Okay, then this is 5 times 2. Circle the pairs. We have one pair. We have not one pair. So then the square root of 20 becomes 2, goes outside, and the 5 stays inside. But this is just the square root of 20. But this is saying 6 times the square root of 20. 6 times the square root of 20. So you see that 6, all we do is we times it by that 12. By that 2. So it just becomes 12 root 5. So if you want, there's identity you can know. So if you have n times, or I'll give you an actual example. So if you have 6 times 4 root, I don't know if it exists, you just times the numbers on the outside. So it just becomes 24 root 10. The same idea here. So this becomes 12 root 5 minus, let's do the 45 one. So this becomes 9 times 5 and 3 times 3. So then this becomes 3 root 5. We have the 2. So it becomes 12 root 5 minus 6 root 5. Now notice when we did that, now we can apply the identity. So this becomes 6 root 5. Do another example. So 3 root 32 plus 5 root 2. Now the 2 is a prime number, so we can't simplify it further. The 32, on the other hand, we can. So we have 8 times 4, and then to 4, to 2 times 4, circle our pairs. The ones that are pairs was on the outside, so 4, and then the one that's not pairs stays on the inside. And we times it by 3, because we did 3 from the beginning. So it becomes 12 root 2 plus 5 root 2 equals 17 root 2. One more. 10 root 3 minus 4 root 75. So let's break this down. So then this becomes 25 times 3. This becomes 5 times 5. Circle our pairs. So then this becomes 10 root 3 minus 4, parentheses, 5 root 3. So this becomes 10 root 3 minus 20. Root 3. So this becomes negative 10 root 3. Great. So, try another one. So the square root of 150 divided by the square root of 6. So 6 is a prime number. Not really. It's not prime, not prime number. It's not a perfect square because it's square root of 3 times 2. So when it's not a perfect square, we can just keep it like that. Square root of 150 though, let's see. Let's break that down. So 150 is 10 times 50. correct. My arithmetic is horrible. 15. There we go. Let's break these two down. So 5 times 2 and this to 5 times 3. Now we can also write that. So this is a pair, this is a pair. These aren't pairs. So this becomes 5, and then we have 2 times 3. So this becomes 5 root 6. We substitute that here. So this becomes 5 root 6 divided by root 6. And this answer just becomes 5. Another one, just for fun's sake. Square root of 72 divided by square root of 8. So let's break these both down. Prime factorization. So square root of 72 is equal to 9 times 8. Break these both down to 3 times 3. This is into 4 times 2. This is into 2 times 2. We have a pair, you have a pair. This is not pair, so it just stays inside. So we have 2. When you have a pair, it's so 2 times 3 times root 2. So this becomes 6 root 2 on the top. Now to the bottom, so square root of 8 is equal to 2. 4 times 2 is equal to 2 times 2. We circle pair, so we get 2 root 2. Then we get 2 root 2. Then we can get rid of these, so then this is equal to 3. Great. So now if we do square root of 12 times the square root of 50, apply a property. Square root, 12 times 50 is what? It's square root of 600. So the square root of 600, does it have a square root? It does not. So let's break this down. So I think 600 divided by 10. So 60 divided by 10. This is 12 times 5. This is 5 times 2. This is 4 times 3. This is, I'm just breaking it down to prime numbers. So we have 2, 3, 5, 5. So we have 5 squared, 2 cubed, 3 to the first, all under square root. This cancels out. This cancels out once. So we have 10 root 6 on, yep, so then this is equal to, so the square root of 12 times the square root of 50 is equal to 10 root 6. We can confirm that because the square root of 600 is 20, and then 10 times, there we go. Another one. So the square root of 27 times the square root of 48. So we apply a property, and we're going to get the square root of 1,296. I don't think this has a perfect square. Oh, it does. So it's just equal to 36. Use a calculator for these. Now, let's do just one more practicing with prime factorization. Let's do a few. So square root of 288. Let's do prime factorization because you don't know what this is. So, square root of 288 on the calculator, it is approximately 16.97 not repeating, could be, well, it's irrational, so it doesn't repeat. Anyway, so it's a decimal. When it has perfect square, means perfect number. So we have to break this down. So let's break it down into perfect squares. 288 divided by 2, which is 144 times 2. This is 12 times 12. 12 times 12. This is 4 times 3. This is 4 times 3. This is 2 times 2. This is 2 times 2. I circle my pairs. 3, 3. And this. So this becomes 2 cubed 3 squared. So again, if you don't understand why I'm circling these, it's because, so when I broke down 288 into 144 and 2, I didn't touch the 2. But I did touch the 144, and I touched that into 12, the two 12s. I didn't touch the two 12s, okay? But I did touch the two 3s. I only touched the two 4s. You see that? So the only ones that are left untouched are the ones that are actually like considered when like writing pairs. So we take the square root of all of this under the square root. The 3's cancel, and the 2 goes out once. So this is going to be equal to 6 root 2. Which is correct. So that's it, really. There's also other things like conjugate rationalizing, but I feel like the hardest thing is, I would say, the prime factorization. So my recommendation is to do a bunch of problems, and remember what's stemming off of what, right? And I guess that's it. And see you later. Have a great day.